To continue our example, we are forecasting GDP growth rates. And some videos ago, we had equation 7, which was an AR1 model, which means that we are explaining the growth rate in GDP by a one lag model. And we can also estimate an AR2 model using OLS, and the regression result is here, and we see that the constant has changed a bit, and the coefficient on the first leg has changed a bit, and we have a coefficient on the second leg as well. And we can also estimate the AR0 model with 0 lags, which is just regressing the growth rate in GDP on a constant, and this constant will be the average GDP growth rate. And you see that if you only have the average and try to explain the GDP growth rate, the R squared is 0. We can use the model to forecast the growth rate of GDP in 2013 Q1. And based on the AR2 model, what is the forecast and the forecast error? And to compute the forecast, we just plug in the values. This is the time period that we are forecasting. So we have to plug in the lag 1 value and the lag 2 value. And we see from our model that we have a constant term of 1.63. We have a coefficient on 0.28 on the first leg, and we have a coefficient on 0.18 on the second leg. So we just plug these in, the constant times, or the intercept, times the coefficient on the first leg times the value of the first leg, and then the coefficient on the second leg times the value on the second leg. And when you multiply and add up, then our forecast is 2.1%. And the actual growth rate in Q1 is 1.1%, so the error, or the forecast error, is the the actual minus the forecast, which is 1.1% minus 2.1% equals 1.0% in negative forecast error. But if we look at how many lags we should include in the AR model, then our candidate models are AR0 model with only the intercept, and AR1 model with 1 lag, and AR2 model with 2 lags. So if we start with the F-statistic method, then we can look at the largest lag, which would be 2 lags, and we have from the model, we see that the t-statistic is 0.18 divided by 0.08. Okay, t-stat. So is this different statistically and significantly different from 0? And we get the F statistic, which is the square of the T statistic, and it's about 5, and it's greater than the critical value of 3.04% or 3.84, and this you find from the F table, and this means that we can reject the null hypothesis of the second leg being equal to 0. So we say that it's different from 0, so we belong, or we keep the second leg in the model. The question here is, where do you find the critical value for the F statistic? Well, if you have 120 more observations than you have parameters in your model, then you can use the F table with infinite degrees of freedom, and you have one parameter that you're testing, which is the last parameter in your model, and that would be the M. So the degrees of freedom of M is 1 because you're testing one coefficient. And if you choose the 5% significance level, then you have a critical value of 3.84, which you compare to your F statistic. In our case, the F statistic was 5, so we reject the null hypothesis of this one coefficient being equal to 0. So that was the answer from the F test. Now we can look at the Bayesian information criteria and the Akaike information criteria. So in our table here, we estimate the model with 0 legs, with 1 leg, and with 2 legs. And the important thing to calculate here is the sum of squared residuals, which goes into this ratio, which you take the natural logarithm of. So these are quite important. These are the first part of the Bayesian information criteria and the Akaike information criteria. And for the Bayesian information criteria, you have the penalty term, which increases for every leg that you add onto the model. So you have the penalty term here for the Bayesian information criteria, and you have the penalty term here for the Akaike information criteria. So, these two are added. So this one and this one are added to form the Bayesian information criteria, and you would choose the Bayesian information criteria which is lowest among them, and you see that the Bayesian information criteria is lower for the second lag model. Because it's downward sloping, you would probably also want to estimate the model for 3 legs as well, because you would keep the smallest or the lag order with the smallest Bayesian information criteria. However, in our model, we have p equals 2, so 2 lags maximum. And for the Akaike information criteria, you would take the log ratio of sum of squared residuals from your estimated model divided by t, and you would add on the p plus 1 times 2 over t, which is the penalty term, and you would have the same decision rule. You would choose the lag order which minimizes this Akaike information criteria. And in our case, both the Bayesian information criteria and the Akaike information criteria, they are lowest for the same lag length, so we choose, based on these information criteria, the model with 2 lag lengths.